Good evening. I wanted to welcome everyone to the San Francisco Java User Group and welcome everyone to Pivotal. Is this anyone's first time here at Pivotal? Well, welcome. We're very glad to have you. Anyone never heard of Pivotal? Well, that's good. That'll make this oh, we do have one, so I can give my little spiel. So we do a couple things. We have a platform as a service offering that's Cloud Foundry. I'm sure most have heard of it. We also have a services arm that does some consulting, moving applications into a 12-factor position so that they can be deployed onto a PaaS cloud. Or for Greenfield, we have labs where we will do app development from the ground up and also work with clients to transform organizations and transform teams so they can function more agilely. So that is most of what we do here. We also contribute a great deal to open source. There's a lot of frameworks that and products. Apache Geode, Apache Tomcat, approximately 70% of Apache Tomcat commits came from Pivotal employees. And then, of course, Spring is probably one of the better known. A couple of housekeeping things. Restrooms are directly behind this wall. I would recommend going down that hallway over there. It's a little bit easier. And then I'm assuming everyone found pizza and drinks and everything are in the kitchen. So without further ado, I will turn everything over to Chris, and we will go from there. My name is Bob Larson.
All right, thanks. So I'm not sure, you guys probably don't know Josh Long, but you absolutely do. I work for Twitter, right? And he's always heckling me that we are not using Spring. I'm sorry. So I'm Chris. I work for Twitter, and I'm going to do a little bit of this today, right? So first of all, and I think in this city, I don't really have to ask, at least I hope. So who has a Twitter account in here? Oh, hey, that's disappointing. I thought everyone would use it. Okay, well, you have to create an account now because I'm asking you to tweet about this session. And then if you tweet about it at the hashtag TwitterVM team, because Twitter actually has a VM team. So I'm going to ask you a bunch of questions because I want to know how familiar you are with Java, the JVM, the JDK. So do people know what a JVM is? Yeah, okay. So I'm assuming that's, do people know what Hotspot is? The JVM of OpenJDK? Yes, you know that. Okay, cool. So we work, basically we build our own JDK. It's a fork of OpenJDK. There's a bunch of additional features and some improvements that are particular for our services. And so that's something we don't upstream, so that's why we build our own. And we have a couple people working in our team now, and I think it's 8 now, so we grew in size quite a bit. We have some GC engineers that take care of all the GC problems that everyone has, and I'm sure all of you do as well. And then I'm a compiler engineer. I do the fun compiler work. And then we have some people working on infrastructure things. Then we have an intern right now who's working on auto vectorization, so a compiler optimization that we are trying to open source them to Graal upstream. And we had an intern, he already left unfortunately, and he was working on a tool called AUTOTUNE. And AUTOTUNE is basically the thing I'm going to talk about today. All right, so a little bit about me, if you don't know me. I'm working on JVMs for a very, very long time already. And all these 14 or 15 years, I was working on JIT compilers. Who knows what a JIT compiler is? Right? So I briefly explain what it is. You might know how the JVM runs Java bytecode, right? It interprets it first, which is very slow. And then at some point, after a few iterations, it finds methods that are hot, that are executed very often. And so then it JIT compiles them just in time. It compiles them to native code. The other compiler category would be AUT, ahead of time compilation, which would be something like GCC, right? Where you compile something, you get an executable, but the JVM, the managed runtime, compiles it while you are running your application. So I was working on JIT compilers, or still am. I used to work at Sun and Oracle in the Hotspot compiler team, so I did a lot of work on OpenJDK. I did a lot of feature work, especially JSR 292, if you know that one, it's invoke dynamic. That's support for dynamic languages. We did that in Java 7. And there were basically two implementations. And one was a lot of handwritten assembly code in the JVM. Hotspot, by the way, is written in C++. And so a lot of handwritten assembly code. And then we realized we had a performance problem. It was very hard to maintain. We had to port it to all the different architectures that we supported. And we had a performance issue in the end. So what we decided to do is to rewrite that handwritten assembly code and move it into Java, into a package called Java lang invoke. You might have heard that before. And so a lot of that Java code in that package I wrote. So if it doesn't work, you could technically blame me. But I'd like to say my code was perfectly fine when I left Oracle, and the people who touched it after me, they broke it. Chap 243, we did in Java 9, and it's the Java level JVM compiler interface. So we also call JVMCI. So do people know what Graal is? Not Graal VM, Graal. No one? Oh, I'm surprised. Okay, so Graal, I think I have a slide on Graal. So let's not talk too much about Graal, but Graal is a new JIT compiler. So Hotspot has currently two JIT compilers. One is called C1 or client compiler, and the other one is called C2 or server compiler. You might have heard the client and server name before, because back in the day we used to use -client -server, but now both of the compilers run at the same time. And Hotspot, as well as other JVMs and other managed language runtimes, do that. They do something called tiered compilation. Do people know what tiered compilation is? All right. So tiered compilation is basically, as I said, you start out running your Java bytecode. It could be from any source language, right? It could be Java, it could be Scala. We run a lot of Scala code, Kotlin, Clojure, whatever. And then you interpret that, which is slow, and then you compile with C1, because the purpose of C1, it's a high throughput compiler. It compiles quickly, right? You want to get away from interpreting code because it's slow. So it doesn't do a lot of optimizations, but it does some. The point is to get to native code as quickly as possible. And the way there are multiple tier levels with C1 compilations, and we compile the code in a way that we also compile in profiling code, so that we collect profiling information while we are running the application. We are collecting how often is a method called, how often are you running a loop, which if-else branch was taken, things like that. And we collect types at call sites, which is very, very important and very powerful. And then later, if you run a while on that C1 compile code and collect data, and then you recompile with C2. And C2, or the top tier compiler, uses that profiling information that you collected, and so it can produce better code than, let's say, GCC can do. GCC has something, if you've heard of it, it's called PGO. It's Profile Guided Optimization. It's kind of the same thing, but with GCC, you have to do 2 runs to actually, get what you want. The JVM is doing this all the time, right? So, and you stepping through the tiers, interpretation, C1 compilation, C2 compilation, that's what tier compilation is. Why did I start talking about this? I forgot. So Graal, yes, right. That's why I started talking about C1 and C2. Graal is basically a replacement for C2, right? It's the top tier compiler in Hotspot, and Graal is written in Java, okay? So the interface that Graal has to Hotspot, because Hotspot is written in C++, we took that interface and extracted it out of Graal so that we have an interface in the JDK. It's there since JDK 9, so you can compile Graal. It's basically a jar file, right? It's Java code. And then you can plug it into JDK 9, 10, 11, 12, because it's the same interface. It's not a stable public interface, but it's stable-ish, right? So we try to not change it too much, but it's not a supported API, basically. And then Chap 295, we also did that in Java 9, and it's ahead of time compilation. So we did that because a lot of customers that Sun and Oracle had, they were always complaining that their applications start up slow. And that's might still be the case for companies who have a big monolithic, application. Then you can have issues with that. In our case, Twitter, and I think a lot of companies do microservices these days. You don't really care too much about startup, to be honest. At least we don't. So ahead of time compilation is basically a small command line utility where you pass in class files or a jar file or something like this, or a Java module, and then it compiles it into native code. It uses Graal, so it reads all the methods in the class files, sends it off to Graal, Graal compiles it, and then it spits out a shared library at the other end. And then Hotspot can pick up that shared library if it finds it. And you're basically skipping the step of interpreting code. If you have a huge application that runs a lot of different code when you start up, this might actually be helpful. Just pointing it out. And now I work for Twitter, best company on the planet. And I shouldn't step on the cable. Is it coming back? Should that be plugged in? All right. Was that the right? Yeah, here we go. That's Twitter. That's what Twitter looks like. So this is from 2016, so it's probably more and bigger now, but we have hundreds of services, right? And then we have sometimes thousands of instances of these services. And on top of it, we run on heterogeneous hardware. So Twitter, we own our own data centers, we own our own hardware, so we kind of know on what hardware we run. But probably a lot of you are running in some form of a cloud, you don't even know what hardware you're running on. And so that makes it difficult to do performance optimizations. Number one, hand tuning doesn't scale, right? So the way performance tuning works today is you sit at your desk at work, and then you're annoyed by the performance of something, right? And then you decide, oh God, okay, I'll tune it a little bit, right? And that happens every 3 years, 5 years, never. So that's an issue. And then on top of it, you can only tune a few parameters, because basically what you have to do is you have to build up a mental model in your head to decide, oh, if I tune that parameter in this direction, what happens and how does it connect to the other ones? This is not easy, and you can only do like 2 or 3. And it's very time consuming, right? And error prone. And the last point is the important one. Upgrades make optimality fleeting. So in today's world, everyone loves agile and everyone deploys 1 million times a day because it's the cool thing to do. We don't really do that, but even some of our services deploy multiple times a week. So that means that the code you're tuning for today is different tomorrow, right? And that means that many services operate below optimality. And that's absolutely true for Twitter as well. So we are throwing out a lot of compute power out of the window, basically, because we're not tuning. So this is a little bit of theoretical part of what performance tuning is, right? You have a function f, and it's defined over domain x. And then what you want to do is you want to find a configuration that maximizes f, whatever f is, right? It could be throughput, it could be memory consumption, it could be reduced CPU utilization, things like that, whatever it is. And then always it's subject to some constraints, right? And the number one most important constraint is it still has to work. And you will see later when I show you all my experiments and the graphs that sometimes you can tune too far so that it doesn't work anymore. That actually happened. Okay, so what is performance tuning, right? You pick some parameters and then you run it on your system and then you measure your F, right? You get it back to a performance engineer, which is a highly paid person in this city. It's very expensive. And that person basically then analyzes what the result was and then decides, okay, I increase that parameter or reduce it. So what we really want is to replace that person with a black box, something. We don't even care what that black box is, as long as as long as it tells us which parameter value to try next, right? So for this black box thing, we're using something called Bayesian optimization. People have heard of Bayesian optimization? Yeah, okay. Don't ask questions because I'm not an expert on this. It's a method to learn potentially noisy, that's important, objective functions iteratively, efficiently, because we would like this to finish rather soon, right? As I said earlier, the code is constantly changing. So if one of these tuning runs takes a month, that's too long, right? We want an answer pretty quickly and then deploy it into production and get the savings. Finds the optimum few iterations, works well with nonlinear multimodal high-dimensional functions. That's the important one. Because the JVM has hundreds of parameters to tune. And as I said earlier, when you do it manually, you can only do 2 or 3 because then your head will explode. But sometimes we want to tune way more than that. And so this thing, AUTOTUNE or Bayesian optimization, you can tune anything, right? I got the question at a conference once where a person asked me, can I tune my database? Yeah, of course you can. You can tune anything that takes command line parameters. You can tune your Minecraft if you want. I don't care, really. All right, so if you want to learn more about how Bayesian optimization works, you should watch one of, or both of them, these talks from my colleague Rumke. He's the expert on all this. He has a very soothing voice, much nicer than mine. So listen to this stuff. The only thing I did, when you look at his slides, I just stole them, right? So, and I'm briefly explaining how Bayesian optimization works. And again, I'm not an expert on this, so that you understand better the graphs and data you'll see later. Okay, we have a parameter that affects performance, goes from -6 to 6, and then the y-axis is performance and higher is better. And the 3 points are actual evaluation runs. These are real data points, okay? So this is the real performance curve, which we don't know, yeah? So what Bayesian optimization then does, when it has a few data points, it just assumes a performance curve that looks like that. And the blue part, above and below the line, is the uncertainty, right? Where we have a data point, the uncertainty is 0 because we know the value, right? And then this is overlaid with the actual curve. They're kind of similar, but not really, but that doesn't matter. What Bayesian optimization then does, it takes the best result, and you can think of it as it puts in a line in the graph. And the blue part above the red line is this graph, the expected improvement. And the more blue you have, the more expected improvement you have, okay? And then it picks the highest one, which is this one, and just gives you that parameter value back, and then you run another evaluation. And so you go through that like this, right? And then you look at the bottom curve, how it changes, and then we go to the left, and then we do this one, and you see the curve that Bayesian optimization assumes gets closer to the actual one, and then we've exhausted this space here, right? So we don't have to run any experiments there. And so we go to one I think to the right, this guy, and that was not very good. So we go to the one on the very left. That was also not very good. And then we go over to the right, and yes, we found this one. And then we continue here and here and here until we've exhausted the whole space, and we found the global optimum. That's what Bayesian optimization does. It's very simple, right? It's basically what you as a human would do as well. It's just cheaper to do it that way and probably faster. All right, that was it. Okay, so we like Bayesian optimization because non-parametric, robust, extensible. The last point is the important one. It's battle-tested many types of real-world high-impact problems. It's been around for a long time. People use this for real things, right? Because we want to trust that. We want to trust the result. We cannot use something, someone just invented, because the goal of AUTOTUNE, and we are absolutely not even close to that point, unfortunately, but our goal is to have AUTOTUNE always on in production for all of our services, that they constantly tune themselves without us having to monitor them. And for that, we need something that works, right? Because we cannot monitor hundreds of services and look at the results if they're better or not. We have to trust what the outcome is. Okay, that was all. Experiments. That's the important and I think interesting part. So what is AUTOTUNE? It basically consists of 2 things. It consists of a BOAS. I should actually write it as a hashtag there. At every conference, I try to get the BOAS hashtag trending, and it never works. So make it happen. It's Bayesian optimization as a service. It's kind of a joke, but not really, because we have something called WetLab, which is a company we acquired a couple of years ago. And it's an enhancement of a framework called Spearmint that's still available as open source. It's just a Bayesian optimization framework. And it's running inside of Twitter as a service. So AUTOTUNE uses it, and then other people use it for other things as well. And then AUTOTUNE itself, you can think of it as a script on steroids, right? Because the only thing it really does is it starts and stops instances of our services and gets F and talks to AUTOTUNE. It's basically like a script, right? It's way more complicated than that. And the reason why we don't have it in production yet is because it's complicated. It always is complicated when you do things in the data center and security and, you know. So, but that's it. That's really it. Yes. So he said you have to talk into the microphone if you want to ask a question.
So I still have a question about the Bayesian optimization.
Oh,
because
no.
You say you can control the parameter of the JVM. However, when you run the program, there are some inputs, the parameters from the program. So how do you run the simulation if you never see the same inputs? How do you control the inputs from the code database, not from the JVM parameters?
I'm not sure if I understand the question. Is the question, how do we get the parameters?
So for the same function in the input, right, you can control some parameters.
Yes.
That is controlled by JVM. But there are still some data flow comes in. Those are come from the user input or something else. So how do you run the same test with different parameters?
I think there's a misunderstanding here. I'm still not sure if I understand your question right, but you're basically asking, you think there's some user input and that would change the performance curve? Is that kind of what you're asking?
Kind of, yeah. Because think about it, when you try to measure a program, but the input is a random number generator.
Sure.
So sometimes if you run the test against some small integer,
sure,
somehow suddenly there's a large one comes in. That change the.
Okay. Now I understand. Okay, so I can answer that in two ways. One is I could go into that, or we just continue with the slides, and then you see two services that I'm tuning. And one of them is the tweet service, and the other one is the social graph service. And then I can kind of explain to you why the user input is not that important. I'm sure there are applications out there where it is, yes, but ours are not. Does that answer it for now? Okay, let's go through the slides, and then if you have more questions, ask later. Okay, what is Graal? We talked about it a little bit earlier, right? It's a JVM JIT compiler. Who knows what a JIT compiler is? All the hands should be up. I explained it earlier. Are you sleeping? Now he woke up. So it's a Java virtual machine just-in-time compiler actively developed by Oracle Labs. So there is something called Graal VM that's now hyped very much because there's something in Graal VM, it's called native image, where you can compile your Java application into a very tiny executable that starts up really quickly. So that's why everyone's excited about Graal VM. But Graal itself is only the JIT compiler, right? So Graal VM basically consists of 3 different technologies, and one of them is the JIT compiler, and the other technologies use the compiler. There's an official OpenJDK project for it. There is all the work is being done on GitHub, so it's all open source except a tiny little part they call Enterprise Graal, where they want money for it. It uses JVM CI, as I said earlier, the interface, and then it's written in Java. For this presentation, it's not important that it's written in Java, but if you're interested in running your applications or your workloads on Graal, I have a presentation that's called How to Use the New JVM JIT Compiler in Real Life, where I do a lot of demos to show you, because the properties of a compiler written in Java and written in C++ are slightly different at this point in time. They will be soft in the future, but if you run with, let's say, JDK 11, and JDK 11 has Graal in it, you just have to turn it on. You have to kind of know that. It's like startup time is a little bit affected. The way it allocates memory is different because C++ allocates with malloc on the native heap, while Java allocates on the Java heap. It's just things you should know if you run your things, do performance benchmarks, and so on. So watch that if you're interested. Okay, so which parameters did I tune? I tuned these 3 parameters. I only did 3 so that we can still understand what's going on. And I picked 3 inlining related parameters. Who knows what inlining is? All right, cool. So for the people who don't know, inlining is basically when you write your code, right, and you have a repeating snippet of code. What you as a very good engineer is doing is you take that and factor it out into a small method, right? It's very nice for you and from a maintenance perspective, but from a performance perspective, it's really not good. So what the compiler does, it undoes what you did. It puts the code back, right? And the reason it does that, compilation, every compiler parses the source language, right? In our case, it's Java bytecode, but it could be, you know, C++ or BASIC or who knows what, into graphs, into compiler graphs, right? Into graphs with a bunch of nodes. And then when we inline more, our worldview gets bigger. And the bigger our worldview is, the more optimizations we can apply. So that's why inlining is the mother of all optimizations, because it enables other optimizations to do a better job. And one of the other ones that's very important is called escape analysis. I'm not going too much into detail, but basically what escape analysis does, when you allocate an object in your method and the compiler can prove that you don't need that object, it's not allocating it. That means your code gets tighter because you're not allocating the object. But more importantly, at the end, it doesn't need to be garbage collected, right? And that makes code run faster, and it brings your latencies down because garbage collections always affect latencies and so on. So we are tuning inlining here to the effect to produce better code and get escape analysis working better. All right, so the first one is called trivial inlining size, and the default value is 10, and it's 10 nodes in the compiler graph, right? So it's not a lot, and we know if a compiler graph only has 10 nodes, it's a very trivial method, and we just inline it all the time. And then maximum inlining size is the other end of the spectrum, basically. But after 300 nodes, we know it's too big, we don't inline it. And then there's one called small compiled low-level graph size, also a default value of 300. It's pretty similar to the second one. The difference is every optimizing compiler has multiple stages, basically. And they are usually called, so the compiler graphs are sometimes called intermediate representation. And there's usually Graal has that and C2 has that too. There's a high-level intermediate representation and a low-level intermediate representation. And the difference between the two is the high level is high and the low level is low. That's how I explain things. Twitter pays me money for, you know, giving you advice like this. It's just a joke. The high one is closer to the source language. In our case, it's Java bytecode. So the nodes in the compiler graph look similar to the source language, while the low-level one is very close to your actual architecture that you're compiling for. So most of us probably x86, right? But it could be ARM or Titanium if you still have one, I don't know. All right, so we're tuning these 3. And I have another talk, which is basically the first part of this one, kind of. It's called Twitter's Quest for Holy Grail Runtime. It tells the story of me starting to work at Twitter, bringing in Graal, starting to run Twitter services on Graal, and what our experiences were. What bugs we found. I explain bugs in this talk, so if you're interested in low-level interesting things, bugs, watch this one. What I did during this talk, I also show what the performance improvement is. What I did during this talk was I did what I said earlier you shouldn't be doing. I was hand-tuning it. And the reason why I was hand-tuning it is I wanted to know if a human can actually tune Graal so that we get slightly better performance. So I'm going to show you 2 slides out of that old deck. And this one, we're looking at GC cycles. This is the parallel GC. And it's unfortunately too many colors. But the blue one, and then I thought JDK9 would be coming out. So this is quite old. JDK9, the Java no one ever used, right? Blue, we're comparing blue and the orange, which is kind of overlaid by the green. You see that here. And by just running on Graal instead of C2, we are reducing GC cycles by about 3%, right? Because that 4.2 is plus the 1.5. The 1.5 is the improvement that I got out by hand tuning it, the 3 parameters you just saw. I was sitting at home on a Friday afternoon tuning it for 3 hours, and 1.5 is nice. It's not a lot, but remember, we're still doing the same amount of work, right? But we're doing 1.5% less GC, 4% less GC cycles. That's actually pretty good. This one is the interesting one because what I'm mostly interested in is reduce user CPU time. That means 11%, 13 minus 2, 11, by just running on Graal instead of C2. So we reduce user CPU time by 11%. This is the tweet service, by the way, by running it on Graal, which means we're still serving the same amount of tweets, right? But we can use 11% less machines. It's outrageous. It's a lot of money. It's way more money than I get paid. And I'm not sure, maybe you guys get paid more, but I don't. And then by hand tuning, I got another 2% out of it. And I was very proud of that. I thought, hey, 2%, it's a lot of money. I'll take it. Probably had a beer that afternoon. I was proud of myself. But you will see later that AUTOTUNE kicked my ass. So these are snippets out of the configuration file. I'm showing you this because of the ranges. So I gave the parameters ranges. You don't have to do that, right? You can say every parameter from 1 to 1,000 or 1 million or whatever, because Bayesian optimization will figure it out anyway. The reason why I gave it ranges is 2. Number 1, I know the service really well. I know what ranges are good. And the second most important reason is I needed this to finish in a certain amount of time to actually fit it on a slide so that you can still see and understand it. So we'll see 24-hour runs, and I was running it for 24 hours. That's why we have ranges. The test setup, very, very important. You have to use dedicated machines. If you're doing performance improvements and you are getting digit percentage improvements, you need dedicated machines, because if you're not, everything you're measuring is noise, right? You don't know what else is running on the machine. Noisy neighbors, biggest issue. We just found out this week that one of the biggest issues with noisy neighbors is the networking card. Yeah, I didn't know that. So I'm using dedicated machines, 1 machine per instance configuration, and then all instances receive the exact same requests. Very important, not the same number of requests, it's the exact same request. And think of the tweet service, right? A tweet could be 1 character long or 280. And the memory allocation for the 2 tweets would be very different. So all the instances receive the same tweet request so that we compare apples to apples. We run that version of Graal, not important. Default tiered C1 Graal setup. You know what tier compilation is now. You know what C1 is. You know what Graal is. It's basically, by default, when you run Hotspot today, you compile C1 and then C2, and we just switch out C2 with Graal. That's all we do. Okay, experiment 1, tweet service. So the tweet service, my favorite one, is a Finagle thrift service. And Finagle is an extensible RPC system for the JVM used to construct high concurrency servers. I have no idea what it is. I really don't. And I don't have to. The only thing that's important to me is, if you look at bottom left, 92% of Scala code. So Finagle is written in Scala. A lot of our services are written in Scala. And Graal is very good at optimizing Scala code. And the reason for this is what I said earlier. It's the escape analysis. Because the way you write Scala, and if you do a lot of functional programming style in Scala, Scala allocates a lot of temporary objects on the way. You cannot really influence that. It's not in your hands. It's doing it behind the covers. But Graal can eliminate these object allocations, and then the program just runs faster. Okay, good. So this is the objective. That's what we're tuning for. And you can see at the end, it says user CPU time, right? So we are trying to reduce user CPU time. But if you remember, Bayesian optimization is always looking for maxima, right? But since we're all really, really good software engineers and we're very good at math, we know how to solve that problem, 1 divided by. Amazing. And then these are the constraints, and there's only 1. It should be more. I only used one constraint, and we run in Aurora on Mesos. And there is a thing called, you see it over there, it's called throttled. So if you get throttled, you're doing something very, very wrong. You're using too much CPU, and then Aurora basically kicks you out. But what these should be is all the constraints that service owners use to know that their service is still well, right? They have that. I didn't have time to do it, so I just used that, and it's fine. All right, here we go. That's the run. 24 hours of tweets. You see, October, it's almost a year ago. And then you see these, blue is experiment, and then orange is the control. And you see these slices. These are 30-minute evaluation runs. 30 minutes is not very long, but again, I know the service really well. I know that in 30 minutes, everything's compiled and it reaches a steady state. And I wanted to fit it on a slide, right? That's the reason. If we would do this actually in production, they would probably be longer. Okay, this is the result, basically. We're looking at the user CPU time. You see again these spikes and the slices. The spikes are when we restart the service. And most of these spikes are cheat compilations. So a tweet service instance compiles about 40,000 methods when it starts up. So that's that. But the majority of the compilations happen in the first 30 seconds up to a minute or something. And then you're basically done compiling. There's some compilations at the end, but the most stuff is compiled at that point in time. And every time the blue line is above the orange one, that's an improvement. Okay. And this is the result you get from AUTOTUNE. You get a web page and a table, and it's sorted by objective. And the top entry is 1.0838, which means that we reduced user CPU time by 8.4%. You remember I got 2. 4 times as much. This is outrageous, 8%. We remember the slide I showed you earlier where we got an 11% reduction by just using Graal, but we get another 8 when we tune it. And then we have a 8.1, a 6.4, a 6.4, and a 5.8. So let's assume the first 2 are outliers, right? So we could guess we get an improvement of 6.4-ish%. That's what I would guess. Here you see the actual values for the parameters. Doesn't really matter. This is the bottom of the table. You can see that 3 evaluation runs actually violated the constraint. That's what I said earlier. We tuned too far, right? We tuned too far. We inlined too much or whatever. The code didn't work anymore. Used too much CPU time, or maybe the compiler took too long to compile. So they got kicked out. One is still running when I shut it down. Then we can, you see the buttons on the top. We can also look at the charts. And this is trivial inlining size. Take these charts with some grain of salt, because every data point in this chart depends on 2 other values that are not the same, right? Remember, we're tuning 3, but it's a 3-dimensional space we're exploring. It's very hard to put that on a 2D slide. So, but we get an idea what's going on, right? You can see there's a tendency going up. The higher the value gets, we get more performance. Default is, what was it, 10? Yeah, default was 10. It should actually be 22, 23. You can see it's going down again. The best one was 21, right? This chart, not as obvious, right? That's the maximum inlining size. There's a slight tendency going up. There are 2 up here that might be outliers or not, right? It could be that just the other values are so much better. Like that configuration is just so much better. Could be. I don't care, right? If it is better, I take it. And this is the last one. It's very obvious what's going on here. So you can clearly see a tendency. The default value was 300, so we're around here. What we should have is about 600, right? So that was the result. And then what I did next was I took the best result from the table, the 8.4, whatever it was, and I deployed it to an instance and let it run for 24 hours. It's basically a verification experiment that I'm doing. I want to see if what AUTOTUNE found actually materializes in the real world. So this is 24 hours of the tweet service. You can see 3 colors or not. The blue one is C2. The orange one is Graal with the default values. And the red one is Graal with the AUTOTUNE flags, right? They all receive the exact same request. That's why it looks the same. And here is GC cycles. In this particular run, we reduced GC cycles by 3.4%. And you can see the fluctuation is how much tweet requests we have during the day. And then we tuned it. You can see it's roughly the same. It's 3.5 up to a total of 7%. It's nice to reduce GC cycles by 3.4%, but if we didn't tune, we would throw away a lot, right? 7% less GC cycles is a lot because, as I said earlier, we're still doing the same amount of work, right? But we're using basically 7% less memory to do the same work. I have this data in a different graph, this one, maybe people understand this better. It's allocated bytes per tweet, right? It's pretty flat during the day because, you know, one character, 280 character, but there's more memory being allocated. It's pretty much the same for every tweet. And it's the same data, obviously. 3.5 and then 3.47% less memory that's being used. And this is the one I care the most about, user CPU time. In this particular run, Graal was 12% better. Amazing, a lot of money. I wish I would get that money. I asked Twitter, they're not giving it to me. And this is AUTOTUNE. And as you can see, it's quite good. It's another 6.2, and you remember I said we could expect a 6.4, which is exactly what we got. So 6.2 up to a total of 18% less user CPU time, which means we could serve the same amount of tweets today and tomorrow with 18% less machines, which is huge in terms of money. And then the other thing I looked at was I looked at P99 latencies for tweet requests because I wanted to know, okay, we're running faster, right? We're using less CPU. We have less GC cycles. Are latency actually getting better? And they are. So it's a little difficult to see how much it really is, but certainly Graal is better than C2. This is AUTOTUNE, and we can tell, yes, it's better than default Graal, but it's hard to see how much it is. So what I did is I integrated over the 24 hours, which is that curve, and then we can see here on the right how much it really is. And it is 20% better just by using Graal, right? And I'm only looking at P99 latencies because if you look at 3 or 4 nines, you're only looking at the longest GC cycle because that affects your latencies then. If you look at 99, that's kind of a real world scenario. It's 99% of the tweets, right? So 99% of the people get their tweet 20% faster. Plus 8, 28% faster. That's huge, right? It means if you would right now pull out your phone and scroll on Twitter, you would get your tweet 28% faster. If you scroll really fast, you can read 28% more tweets, which I would really appreciate because that brings the stock price up. All right. So experiment number 2, social graph. I did another one because it's also a finagle thrift service, very similar to the tweet service. This one is an abstraction for managing many-to-many relationships at Twitter. So it's basically who follows you, who are you following? That's what social graph does. And most of our services use Finagle, and Finagle uses Netty. So the stack is more or less Netty, Finagle, and then the logic of the service itself. That's the only difference, basically, right? And you will see what the difference is between performance improvements. You've seen that before, nothing new, same objective. We're trying to reduce user CPU time, same constraint, let's not get throttled, and this is the run. So 24 hours of social graph requests per second, same thing, 30-minute evaluation runs, that's the result. Not a lot to see here, it's hard to interpret, that's the table. And the top one is 7.6, which is good, right? And then we have another 7.6, a 7.2, a 6.8, a 6.4. So maybe we'll get a 7% improvement, right? That's what I would guess. Bottom of the table looks like that. One that violated the constraint. Don't look at the 3 that are still running, it's a bug. And the charts look like this. Similar to the tweet service, maybe not as obvious, but you can see it found a 23. So I would guess for our code base, because it's the bottom of the stack is very similar, this should be around the 21, 22, 23 number. This one, there's a slight tendency going up. The best one is somewhere there around 400. Sure, why not? And this one, not as obvious as for the tweet service, but certainly a tendency going up. The interesting thing to point out in this one is, I'm not sure if you paid attention, but the range for this one was, I think, 200 to 650. And this is like 649 or something. So if I do the experiment again and I pick bigger ranges or no ranges, I might actually get a better result here. But it's good for now. All right, verification experiment. We do the same thing. We run it 24 hours. Pretty much similar, yes.
So did you just find like an optimization that everyone could use for the Graal compiler? Shouldn't everyone use 22 instead of 10 and 600 instead of 200?
Possibly, yes. I'll show you something in a minute that will show you something that might even be more interesting to you. So social graph is using CMS. So we're looking at part news cycles here. And this is just, the code is just different, right? So we can reduce GC cycles by only 1.6%. It's just how your code looks like. If the compiler cannot eliminate as many objects, all right, that's what it is. But interesting is, you can see already the difference here with AUTOTUNE. We tune by 3.5%, which is twice as much as we get out of Graal by default. So if we wouldn't be tuning, which no one in this room is, this is what you're throwing away, right? So up to a total of 5, absolutely take 5% less GC cycles. This is user CPU time, and the 5 is, no, the 1.6, right? The 1.6 is roughly half of what we have for the tweet service, if you remember. And user CPU time is only 5.5, which is roughly half of what we got from the tweet service. If you remember, it was like 12. So these kind of correlate, right? If we can't eliminate as many objects, we also can't save as much user CPU time. Okay, this is AUTOTUNE. Certainly an improvement, you can see that. Interesting also because when we tuned, we reduced by way more GC cycles, so way more objects could be allocated. That also gives us more CPU savings. So again, we save more here when we tune it than not. Interesting to point out in this one, you might have noticed, is when you look at the blue and the orange line, the improvement is the same over the day. It doesn't matter if the load is low or the load is high. But the red one is actually better when it's high. That should not be the case. And I don't have an explanation for it. And I don't have the data anymore, so I can't go back and look. But it should be the same over the day. Right? Questions? Okay, you all, if you paid attention, and you know, when I explained C1 and C2 and everything, everyone should have this question. Right? Did I do an AUTOTUNE run with the current JIT compiler C2? And of course I did. Right? I couldn't come up here and say, well, Graal is so cool and everything's so cool. When no one's using it, I would like you to use it, right? But right now, you are not. And you are using C2. So let's do tweet service tuning with C2. We tuned these parameters, these 3, and I tried to find parameters that are very similar to the ones that we tuned for Graal. Max inline level is the value, default value is 9. Graal does not have that, but it's a very important flag because it basically determines how deep inlining goes, how many call levels you inline. And at 9, it stops. It's a hard stop. And that's a big issue today. We picked 9 probably 15 years ago, right? 15 years ago, the code was very different than today. Today, everyone's using a trillion of frameworks. Framework A is calling framework B, calling C. At 9, it stops. You're even not even yet at the code you wrote, right? So, and then we have max inline size. That's very similar to the one we had in Graal. Default value 35. The difference between this one and the Graal one is the Graal one was nodes in the compiler graph, right? This one is bytecode size. It's odd, but sure, why not? If you ever had code and, like, let's say performance critical code, and you added assert statements to small methods and suddenly your performance went to shit, because of this guy. Because, and it's very embarrassing, C2 does not discount for assert statements. Assert statements show up in the bytecode. They're just not compiled, right? But they count to the bytecode size, and C2 is not discounting for them. Big problem. But I'm sorry, use Graal, right? Doesn't have the problem. This one, inline small code, 2000 is a very odd one. It's 2000 bytes of native code, right? So basically the reasoning behind it, I think, it was introduced before I was at Sun. The reasoning behind it is if you want to inline a method and you already have compiled code for it, and it's bigger than 2000 bytes, you probably don't want to inline it because it's big. I can understand that to some degree, and maybe most of the time it's true, but not always, because if you inline, a lot of things can fold away, right? You don't have to pass parameters around it. The compiler can see, oh, this object is actually, I can eliminate that, right? So a lot of things can be enabled when you inline more. So this is an odd one. So I tried to tune it. All right, what ranges? Not sure if you're interested, but same thing, right? I wanted to do it in 24 hours. That's the run. Again, 30-minute evaluation runs, 24 hours of the tweet service. That's the result. Certainly better or some are worse. Here's the table. The top one is 5.1. That's pretty good for a JIT compiler that's been around forever. And tuning it and getting 5% more is absolutely good. 3.8, 3.5, 3.3, and a 3. So let's assume the first one is an outlier, and we get maybe a 3.5% improvement. That's good, right? Remember, I'm talking a lot about Graal and how cool it is, but remember this talk is about AUTOTUNE, right? So AUTOTUNE absolutely does its job, right? You can tune your stuff today when you run on C2 with that, and you'll get a performance improvement. The only difference is 3.5 compared to 18, right? I'd rather move to Graal, to be honest. Okay, the bottom of the table looks like this. No constraint violated. Yeah, that's all to see. The charts look like that. That's max inline level. Everyone can see what's going on, right? The default value is 9, but it should be 8, 17, 18, something like that, right? Twice as much. And that's the thing I was talking about, right? If you want to tune something today for your application, just set that one to 18. And I'm sure it will give you an improvement. This one, max inline size, is flat. That surprised me, right? Because if you remember, it's basically the same flag as the first one for Graal, where we clearly could see an improvement in performance. This doesn't affect performance at all, right? That one, the best one, is an outlier, but everything else is like flat. And the last one, the weird one with the compiled code size, is also flat. And that did not really surprise me, because not happen a lot that that's the case. And so, you know, and then they're big and they're not being inline. So, all right, I can understand that. I did not do verification experiment for the C2 case, but as I said, if you want to tune something, tune the max inline level. Or, much better, move to Graal, right? And get way more for free. So the summary of my talk is the same as for all of my talks. It's very long. It's that. That's how you turn on Graal in OpenJDK. If you're running on OpenJDK 10 or later, so 11 would be the LTS. Everyone's running on 11 in production today, right? Excellent. So we are not. Is it still working? Yes. We are running on Java 8. There is a way, if you are on 8, you can download the Graal VM Community Edition, which is free to use in production. It's basically what we are doing, right? We just ported JVMCI and Graal ourselves to OpenJDK 8. But Graal VM is kind of the same thing, right? And then you can run with Graal. I would really, really suggest that you give it a try, right? For Scala code, you can see it does a much, much better job. And for Java code, it's like a mixed bag a little bit. It's a 50-50 chance if your code runs faster or not. And the reason for this is C2 has been optimized for Java code for years, right? I've worked at Oracle, at Sun and Oracle on C2. Not a single day, a single hour, a single minute did we optimize for anything else than Java, right? So if you run on a different language, Scala, Kotlin, Clojure, Groovy, whatever, you might want to give Graal a shot. So C2 is highly optimized for Java code, especially all the inlining heuristics and everything. But more importantly, the code you wrote, the Java code you wrote, is optimized for C2, right? You wrote it in a way that it runs best on C2. It's very difficult for a new compiler to come in and be better everywhere when you tuned your code for a specific one. Give it a shot. Let me know how it works. The best way would be on Twitter. If it works for you and it runs better, great. Buy me a beer next time and let me sleep at your house. If it crashes for you, perfect. Because then we found a bug, right? And if you find a bug, Oracle Labs, they would be happy to fix it for you. And we don't find it. And if Twitter's down, everyone's sad, right? Because when Facebook and all the other ones are down, they come to Twitter and say, oh, everything's down. But we up. That's because we do cool stuff with Graal. And if it's slower for you, that could certainly happen, right? Please let us know, right? Because then we want to see why it's slower, and we want to improve Graal to also run about the same speed as C2 or better. So this might be sometimes tricky because you might have proprietary code at your company, but maybe you can extract a test case or something and send it to us or Oracle or whoever, and we'll take a look why it's slower. All right, I think that was it. I think we do questions now.
So since you had a familiarity with assembly, have you looked at some of the actual optimizations in assembly code and been like, oh, that's a cool way to optimize, when you've seen the optimization that the system did on certain paths of code?
You mean optimizations that the compiler does?
No, on the, yeah, I guess that's right, yeah.
I'm not sure I understand the question. So you're talking if I've seen optimizations in the compiler where I thought, oh, that's cool.
Yeah, I guess that was my question.
Okay. Well, yeah, everything's cool, but I kind of know how they work. Or do you want to know about the actual algorithm and implementation of it, or the outcome? Right. Yeah. No, I mean, there are a bunch of compiler optimizations. I'm every now and then I'm thinking about doing a talk where I explain all the compiler optimizations. It's something that you don't have to know, but it would be nice to hear once and then forget the next day. Right. Yes.
Hi. So with this parameter optimization, you showed us 3-4 parameters you optimize in production, or like how many parameters you can optimize with this method?
As many as you want. Depends on how much time you have.
I see.
Right? Because if you remember, the more parameters you tune, the more n-dimensional your space gets. Right? Yes. If you want to tune 1,000 parameters, it will take some time. Right? But you could, for fun, but at some point you will figure out what are the ones that actually affect the performance of my system, right? Or maybe you have parameters that you put into your system where you know, oh, this one would affect performance or something like that, right? So I picked the 3 inlining ones. There are not many more than 3 that would affect inlining. You know what I mean? So, and for the GC, I'm doing a part 2 of this talk right now, where I tuned the compiler and the GC. And for the GC, we tune, I think, 4. So it's not, infinite, really. I mean, technically, yeah, but not really.
Thanks.
Graal also supports ahead of time compilation, but you didn't mention that one here. Is just because it's not going to work because all the compilation is just static at that point?
So you're talking about native image. Yeah. So native image is the command line name for a technology called Substrate VM. That's the thing behind it, Substrate VM. And what Substrate VM does, it's number one, right? I talked about, you remember CHEP 295, the AOT compilation that we did. It's not the same, right? It's different. So CHEP 295 is in OpenJDK, and it is Java, while Substrate VM or native image is a subset of Java. It's not fully Java compatible because some things you can't do, right? You can't do dynamic class loading when you compile to a static executable. So a lot of people are very interested in Substrate VM native image now because everyone thinks function as a service and serverless is the coolest shit on the planet. And it starts in milliseconds, right? That's why they want it. And for short running things, it's perfect. Do it. I mean, it's basically the goal of native image is to be a replacement for Go. And so if you have something that's short running, absolutely use it. Our services are not short running. Our services run for at least a day or longer, right? It's most of them, some of them we deploy multiple times a week, as I said, and then some are deployed once a week, some are deployed every couple months, right? So our things are long running. And we are basically, when we're not CPU bound, we are memory bound. As you might know, the JVM hotspot has, I don't know the current number, but multiple GC implementations, right? And you pick the one depending on your workload. If you want low latencies or throughput or whatever, you pick parallel or CMS or G1. Substrate VM has one GC, and it's the most stupid GC implementation on the planet. It's not even parallel, right? It's a non-moving, as far as I know, non-parallel collector. So if you're memory bound, this doesn't work for you. And we are memory bound, so it doesn't work for us. That's why we're not using it. But the Substrate VM uses Graal to compile code, right? That's how they are linked together. We just use the compiler and the JVM. Questions? No? Yes? Microphone?
A very important one. Where does the name come from?
So it's the German word for Grail, right? And I think, I'm not even sure when they picked it. It was probably the Holy Grail, the Holy Graal. A little bit of history on the project is, it started out as a one-to-one port of C1. So C1, the compiler, is written in C++, and it was a port to Java. It was called C1X. And then they mainly did that because they wanted C1X in Maxine. I'm not sure if you heard of Maxine. You might have heard of Chike's RVM or Jalapeno. That was the first name. IBM had a JVM that was written completely in Java. That was Chike's RVM. And Oracle Labs had the same thing, and it was called Maxine. So everything is written in Java. So the whole runtime system, the compilers, the GC, everything. And they wanted a better compiler in Maxine. That's why they ported C1. And then after a while, they realized, oh, we have to do more optimizations and other things. So C1 is not, the structure of C1 was not suitable. The intermediate representation was not the right one to do a lot of optimizations. And then at some point, they renamed it. Yeah, I guess. I'm not sure why. I've never asked. All right. Yes?
I have a question that might be beyond the scope, I guess.
Sure.
But I'll ask because what I wanted to know was, is it possible to also like boil down these performance improvements to, let's say, like precise like line numbers or the method calls or something like that? Like how feasible or how stupid is? So essentially like assigning that these are the things that are actually causing the inlining to perform better.
Right. So sometimes you can. So let's pick an optimization that's called auto-vectorization, right? Auto-vectorization, basically it vectorizes loops, right? If you do matrix multiplication in a loop or something, it can vectorize that to use SIMD instructions. So you could track that down, oh, that's that loop, right? But for other things, let's say escape analysis, you can't really, right? And then especially for escape analysis, you would know everything that gets in line to actually know if the object you're allocating on this line will be eliminated or not. So related to that, sometimes there are hecklers, right? And at one conference, a guy after the talk, he said, well, I mean, 12% is really nice, but if I tune my application, I get. I thought, yeah, okay. You can do that too. Tune your application. Everyone needs to ship features, so not everyone has time to do performance improvements on their code all the time, right? Because your code is changing all the time. And then on top of it, we have hundreds of services, right? Not every team could tune their code. So that's something to consider. It's additive, right? You can still make your code better. If there is, the thing I always tell people, when it comes to writing Java code, I don't know Scala too well, but especially Java, that one I know good. Don't be too smart, right? Don't micro-optimize things, because the reason is the compiler is just a state and pattern matching machine. It doesn't have AI, right? It cannot think. So what it does, it matches on patterns. So write your Java code as it's supposed to be written, right? Source code is meant to be consumed by humans. It's there for you to understand and write it in a way that it's maintainable. If there's obviously a better algorithm for the thing you do, sure, use the other one. But don't do bit twiddling and things around and micro-optimize things. There's a story I know. I joined Twitter, and they didn't have a compiler engineer before me. So I joined Twitter, and then someone told me the story of a team. I don't know the name, actually. I wouldn't say it, but I really don't. They had too much memory pressure, too much garbage on the heap, too many GC cycles. So they optimized their code to allocate less memory, right? So they got rid of object allocations and rewrote code, and I don't know exactly what they did. It took them a few people 3 weeks to do that. And in the end, the improvement was 0. Because the compiler already did all that. So write your code that you can understand it and you can maintain it. Leave the rest to us. That's what I can say to that. Yes?
I guess a very basic question, but why not to compile to native code? Because I guess, I mean, probably you, Twitter, and many companies run really on the same platform, same hardware. So why not to upfront compile to native code?
Yeah, sure. Valid question, absolutely. One of the things is, so the only way to AOT compile would be substrate VM. That's basically what I said earlier. Since we're memory bound, that's a no-go to begin with. The other thing is, it's not true that we're running on the same hardware. Right? Newer generations of chips have newer versions of SSE and AVX, and so what you have to do is, does anyone still do Gen 2, the Linux thingy? No, was that Gen 2 where you compile everything from scratch? Because if you install Linux on your machine, it's built for the lowest denominator instruction set. Right? You can't compile for things that only a few of your machines have, because your thing will crash. So it's not that easy, right? And what the JVM does, since it compiles stuff on the fly, it knows what your CPU can do. So it uses all these enhanced instructions, while AOT code would not. And we'd rather spend, I just said this yesterday, a minute is already outrageous, right? But I would rather spend a minute longer to start out our service and then save for 24 hours, right? It's all about, all right. More questions? Cool. Thank you.